Now let's come to a practically relevant but still sufficiently simple class of operators for which we can explicitly compute the spectrum. But let's start from the beginning. We start with a two-sided infinite sequence of numbers, and let's assume that only finitely many of them are non-zero. And then look at the following infinite matrix, which is the so-called Laurent matrix that corresponds to our sequence A. And this is a two-sided infinite matrix, and on its main diagonal, every entry is equal to A0. On the first sub-diagonal, every entry is equal to A1. On the first super-diagonal, every entry is equal to A-1, and so on. Some people would also call this a Toeplitz matrix. In this case, it's a two-sided infinite or bi-infinite Toeplitz matrix. And then you treat this infinite matrix as a linear operator on the L2 space of two-sided infinite sequences. And this operator would then be called a Laurent operator or convolution operator. And now let's see how it acts on an L2 sequence. So you take a two-sided infinite sequence X from L2 of Z and apply your convolution operator to it. And then you get another L2 vector, let's say Y, where the ith component of Y is just computed like in usual matrix times vector multiplication. You're just multiplying the ith row of your matrix by the column X. And of course that involves the summation of all integers. And now here Aij denotes the I, j entry of that infinite matrix. But if you look at this matrix long enough, then you see that the I, jth entry is just ai minus j, when now a refers to the entries of our sequence. So I'm sure you can distinguish between the matrix entries that have two indices and the sequence entries here that have just one index. And for example, you see that along the main diagonal where I equals j, you just get a of 0, which is exactly what you have. And then one diagonal lower where I is just one bigger than j, you get that aij equals a1, which is exactly what you have. And like that, you can proceed. Okay, so instead of aij, we could substitute ai minus j. And then you do that for every little I in Z until you have all the entries of your vector Y. And I'm pretty sure you've seen this operation before. So that takes an infinite sequence A and an infinite sequence X and twists and turns them in a way and sums up to give you another infinite sequence Y. And typically you would call that the convolution of the vector or sequence A and the vector or sequence X. And the standard notation for the convolution operation is just this little star here. Okay, that of course explains why we call this the convolution operator. It just convolves X with this fixed sequence A. Convolution in German is Faltung. Well, maybe you recognize it now. Okay, let's look at some simple examples, and maybe then you believe me that convolutions are everywhere. Well, first of all, the identity operator on little l2 is just operator of convolution by this sequence here. So let me mark the 0th entry of my infinite or bi-infinite sequences by a little box, so we can all see where 0 is. Okay, so it's clear that on the main diagonal you have this 1 here, and on every other diagonal there's 0. Nothing more to say about this. Second example, the forward shift, let's denote it by F. And we saw it many times before, the corresponding matrix has zeros on the main diagonals and ones just below the main diagonal. And this is the operator of convolution by this sequence. So also this sequence just has one entry equal to 1, and that corresponds to the first sub-diagonal. So it's sitting at position 1. Well, and similarly, the backward shift, let's call it B, just shifts in the other direction. So now the 1 is sitting in the minus first position of my sequence A, and all the rest is still zeros. Okay, maybe let's try something a bit more substantial now. Let's look at the discrete Laplace operator in 1D, where, to be honest, Laplace in 1D just means second derivative. Okay, and discrete here means that you actually sample your function f over a discrete, probably equidistant grid, and that the approximation to the second derivative at the kth data point can be computed by finite differences, where here you approximate the first derivative of f at the next data point k plus 1, and then you do the same at your data point number k, take the difference and divide by the grid size, so the distance between two grid points. Let's call it little h. But then to approximate the first derivative at some kth or k plus first data point, you would just take the difference of two data points of f and divide by the grid size again. And that's how you arrive here and then here. Maybe you have noticed that we are using forward differences for the second derivative, so that's in this big difference here, and then backward differences for this first derivative in these small differences here. But that's just to be fair, so we don't shift focus too much to the right or to the left. So if you spell it all out, you get 1 over h squared, because you're dividing by h here and also here. Okay, and then you have fk plus 1 minus fk, and again minus fk, and minus times minus is plus fk minus 1. Okay, and this is exactly the operation that you get by applying the following matrix. Well, before we forget, let's divide by h squared. And then you put a minus 2 on the main diagonal, so that every fk that comes in gets multiplied by minus 2. And then you put 1s on the first sub and super diagonal. That corresponds to the ones that you find here and here, which work with the previous and the next data point. Okay, well now this is obviously the operator of convolution by this sequence here. So you have 1 over h squared, and then your minus 2 in the 0 position, and a 1 to either side of it. You can see that this is a self-adjoint operator, so the adjoint of this is just the operator itself, so the spectrum should be on the real axis, and we will see all of that coming. Maybe that's enough examples for the moment, but here's just a short message afterwards. You should keep in mind that convolution means you have constant diagonals, and that corresponds to so-called translation invariance, where translation invariance means whether you shift your vector before, let's say with the forward shift, and then you apply your operator A, or whether you first apply the operator A and then shift by the same f, you get the same result. And of course we know that property, for example, from differential operators. Whether you shift your function a little bit to the right and then take the first derivative, or whether you first take the first derivative and then shift up one a little bit to the right, you get the same result. And that's not just the case with the first derivative, it holds for all derivatives in all dimensions. And that explains why we find so many differential operators here in this class of convolution operators. By the way, talking about this, we could of course express the discrete Laplacian in terms of the 3 operators that we saw before. Maybe this would be nice to do. Okay, excellent.